So Friedel-Crafts alkylation is great for putting tertiary alkyl groups on benzenes, but not so good for getting nice clean syntheses of primary and secondary alkyl groups on benzenes. How do you do that? Well, you don't use Friedel-Crafts alkylation, you use Friedel-Crafts acylation. Now I've put extension here because the WJEC does not talk about acylation, but I do believe that some of the English boards do. So it's here in the core material, also because it kind of wraps up the story nicely. Anyway, we haven't talked about acyl groups yet, but here is an example of one. We'll be talking about that in about 2 or 3 modules time. So you have a carbon. It's got an R group on it, so I've got the R and the C in blue because that's going to be, we hope, ultimately the alkyl group we're going to add on. You have a double bond oxygen here, and of course there's the chlorine. Same catalysts, right? So in this case I'm using aluminium chloride, could use ferric chloride. This works quite well for the brominations as well, so Br and Al or Fe, Br3. So the usual thing, there's our starting material, there's the aluminium chloride catalyst. Electrons come from a lone pair on the chlorine, making a bond to that aluminium. We get this complex here. Now at this stage, of course, we have a carbon that's got this double bond oxygen on it. And so that carbon now can say to this chlorine, why don't you take those electrons and break that bond, just like we saw for the tertiary carbocation formation. Okay, and here we make an acylium cation. Okay, this carbon here that is actually an extremely powerful electrophile and also a relatively nice, happy little intermediate. Okay, so carbon with the positive on it, but there's no rearrangement going to be going on here because this carbon is double bonded to the oxygen. Now in the extension material I'll talk a little bit more about how we can demonstrate that while this looks like it shouldn't be a very happy intermediate, it's actually stabilized by so-called resonance, but I don't want to get into that here. I'm just going to say this is a nice happy little electrophile and it doesn't undergo rearrangements. So now of course you know what's happening. That's our benzene, that's our electrophile. 2 electrons pop in from the pi bond, making the bond to the electrophile, so we end up with this rather complicated looking species. The aluminium tetrachloride, the AlCl4 minus, comes up, grabs the proton, abstracts the proton. The 2 electrons from the carbon hydrogen bond go to replenish that carbon double bond, and we get this species here with HCl and AlCl3 formed again. So exactly the same thing we've seen several times now, except now we've got an acyl group on the benzene. Well, that's jolly good, you said, but how does that help us as far as getting alkyl groups? Well, one can reduce that acyl group, and one of the most popular ones is to take this acyl benzene, stew it up, not very hot temperature actually, with a zinc mercury mixture. Anytime you have a mixture with mercury is called a such and such amalgam. So this is a zinc amalgam with HCl. That is a nice effective reducing agent, and so you can see that we have lost oxygen, gained hydrogen, nice little reduction, and we've made ourselves a nice primary alkyl group on the benzene without having to worry about any kind of rearrangements. This is known as the Clemmensen reduction. So Friedel-Crafts reaction is very useful for getting alkyl groups onto benzene rings. Very good straight off with using the alkyl halides when you want to have a tertiary group on it for tertiary alkyl halide. Primary and secondary, actually much better to go through Friedel-Crafts acylation followed by reduction. In this case we use the Clemmensen reduction.